Alright, in this video I'll be solving paper 31 for May-June 2024. So make sure to like the video, subscribe, and let's dive right in. Number 1. Expand 3 plus x times 1 minus 2x to the half in ascending powers of x up to and including the term in x squared, simplifying the coefficients. So we've been given 3 plus x multiplied by 1 minus 2x to the half, and we're told to expand all of this up to and including the term in x squared. So what that means is that we have to first expand this up to and including the term in x squared. Then we'll replace this bracket with its expansion. So let's work on that bracket. That's 1 minus 2x to the half, and we'll use the formula for binomial expansion where n is a fraction. So that's 1 plus n times x, be careful, the negative sign there, that's negative 2x plus, that's half, times half minus 1, and this is all over 2 factorial multiplied by negative 2x squared. Alright, so this simplifies to 1 minus x, the half and the 2 cancel out, and then let's evaluate the coefficient of our term in x squared. So that's half times half minus 1 over 2 factorial times 2 squared, and that gives us negative 1 over 2x squared. Alright, so this here is the expansion of this bracket. So we can replace that bracket with its expansion so that we get 3 plus x multiplied by 1 minus x minus 1 over 2x squared. And now we want to expand these two brackets up to and including the term in x squared. Alright, so we can start by multiplying the 3 by 1 to get the term independent of x, and then 3 times negative x, that's the term in x. We can also get the term in x by multiplying x by this one over here, so that's plus x times 1. And finally we have to get the term in x squared, so we can get that from saying 3, which is here, multiplied by the negative half x squared, so plus 3 times negative half x squared. And then we can also get it from multiplying the x that's here by the negative x, so plus x times negative x. Now we're not going to multiply this x by the negative half x squared because that gives us a term in x cubed. We have been told that we want to expand up to the term in x squared, so that's where we'll stop. So now let's just simplify our coefficients. We've got 3, this here becomes minus 3x plus x, then we've got minus 3 over 2x squared minus x squared, and simplifying like terms we get 3 minus 2x, that's minus 1.5 minus 1, so that's minus 5 over 2x squared, and this here is our final answer for question number 1. Number 2. Solve the equation ln x minus 5 is equal to 7 minus ln x. Give your answer correct to 2 decimal places. Alright, so that's ln x minus 5 is equal to 7 minus ln x. So I'm going to put all the natural logarithms on one side so that this becomes ln x minus 5. Move that to the left, it becomes positive ln x, and this is equal to 7. Alright, and then here we are going to use the law of logarithm that says that ln a plus ln b is equal to ln a b to simplify our logarithms on the left hand side. So this becomes ln x minus 5 multiplied by x, and this is equal to 7. So in fact, let's just expand that. So x times x gives us x squared, x times negative 5, that's negative 5x, and this is all equal to 7. And now to get rid of our natural logarithm, we're going to apply the exponential function to both sides. So this becomes x squared minus 5x is equal to the exponential of 7. Alright, let's move everything to one side. So that's x squared minus 5x minus e to the 7, which is equal to 0. And this here is a 3-term quadratic, so we can use the quadratic formula to solve our quadratic. X is equal to minus b, so that's 5, plus or minus the square root of 5 squared minus 4 times a, which is 1, times c, which is negative e to the 7, and this is all over, that's 2 times a, so 2 times 1. Let's punch this into the calculator. That's 5 minus the square root of 5 squared minus 4 times 1 times negative e to the 7 all over 2 times 1. And this gives us negative 30.70968 and so on. And then the positive one gives us 35.70968 and so on. Right, now here they're telling us give your answer. Answer is singular, meaning that we should only have one solution here. And so we need to disregard one of our solutions. So if we come back to our original equation here, you notice that we have ln x. We know that ln x can only take values of x that are greater than 0. So it means that in this case, this negative 30, if you substitute it into ln x, you get an error. So it means that it's not a possible solution. So we can conclude that therefore the correct answer is actually the positive one. So that's 35.71. I believe they wanted to 2 decimal places. Yes. So our final answer would be x is 35.71. Number 3. The variables x and y satisfy the equation a to the y is equal to bx, where a and b are constants. The graph of y against ln x is a straight line passing through the points 0.336, 1.00 and 1.31, 1.50 as shown in the diagram. Find the values of a and b. Give each value correct to the nearest integer. So we're given that our variables satisfy the equation a to the y is equal to bx. So we have to reduce this equation to the equation of a straight line. So to do that, we can apply the natural logarithm to both sides. So this becomes ln a to the y is equal to ln bx. And then on the left hand side, we are going to use the law of logarithms that says log a to the n is equal to n log a. So that means what we end up with here is y ln a, and then on the right hand side we can use the law of logarithms that says ln a plus ln b is equal to ln a b. Okay, so it means what we end up with, we are actually moving in the opposite direction. We end up with ln b plus ln x. Okay, and then we are going to divide both sides by ln a because we want to make y the subject of the formula. So this becomes y is equal to ln b over ln a plus ln x over ln a. Now I'm actually going to swap the order of these two so that it's ln x, and in fact I'll just factor out the 1 over ln a, which I'll explain in a moment, plus ln b over ln a. Right, Now we want to compare this to the equation of a straight line. The equation of a straight line can be written in the form y is equal to mx plus c. Alright, and we have been told that our line should be y against ln x. Be careful here, they're saying it's against ln x. You're used to having your line being y against x, but in this case it's actually ln x, so be careful of that. So going back to the equation of a straight line, we're saying that in this case our gradient m should be this part here, this 1 over ln a, since our line is y against ln x. In this case it's y against x. And then our y-intercept c should be this part here, ln b over ln a. So what we can do is that we can find our gradient. We've been given 2 points here, these 2 points, so we can find our gradient m by saying the change in y, which is, we'll do 1.50 minus 1.00 over the change in x, which is 1.31 minus 0.336. So m is equal to, let's punch that into the calculator, 1.5 minus 1 over 1.31 minus 0.336. This gives us 250 over 487. This is our gradient m. Going back to the comparison we made to the equation of a straight line, we're saying our gradient m is the same as 1 over ln a. So since we know what m is, we can say that 1 over ln a is equal to 250 over 487. Okay, so what this means is that ln a is equal to 487 over 250, and we can solve for a by applying the exponential function to both sides. So a would be the exponential of 487 over 250. A is equal to, let's punch this into the calculator, e to the power of 487 over 250, and this is, we wanted to correct to the nearest integer, but I'll just give the calculator display for now, 7.014644253. This is what a is. Alright, and then we also need to find b. We can get b from the y-intercept, right? So we're saying the equation that we have is y is equal to 1 over ln a multiplied by ln x plus ln b over ln a. Alright, so now we're going to pick a random point that lies on the line to help us evaluate our y-intercept. So we can pick this point where our ln x is 0.336 and our y value is 1. Remember, our graph is y against ln x, so it means that this first part here represents ln x and not x, and then the second part, the 1, represents y. Okay, so let's substitute that into our equation. So our y is 1.00, and this is equal to 1 over ln a. We said 1 over ln a is the gradient, and this is equal to 250 over 487. So 250 over 487, and this is being multiplied by ln x. We said our ln x is 0.336, 0.336, and this is plus ln b over ln a. We already know from above that ln a is 487 over 250. So this is being divided by, let's extend this, 487 over 250. Okay, so let's just simplify this. This is 1 is equal to, we've got 250 over 487 multiplied by 0.336, and that gives us 84 over 487 plus, if we resolve our fraction there, that's 250 over 487 ln b. Okay, and now we have to solve for b, so that becomes 250 over 487 ln b is equal to 1 minus 84 over 487, which is 403 over 487. Let's make ln b subject of the formula. Ln b is equal to, that's 403 divided by 487 multiplied by 487 divided by 250, and this is 403 over 250. And now we can simply apply the exponential function to both sides, so b is equal to e to the 403 over 250. b is equal to, let's punch that into the calculator, that's the exponential of 403 divided by 250, and this gives us 5.012826863. Okay, we have been told that we should give each value correct to the nearest integer, so we can conclude that therefore a is equal to, what is a to the nearest integer, a would be 7. So we're looking to put this to the nearest whole number, and then b here would be, that's 5, so b is equal to 5, and this would be our final answer. Number 4. The complex number u is given by u is equal to -1 -I root 3. Part A. Express u in the form r cos theta plus I sin theta, where r is greater than 0 and theta is between -pi and pi. Give the exact values of r and theta. Alright, so we know that r represents the modulus of our complex number. So to find r, we simply have to find the modulus of u. So we're saying r is equal to the modulus of u, which would be the square root of, that's -1 squared plus root 3 squared. So let's punch that into the calculator. The square root of -1 squared plus root 3 squared, and that gives us a 2. So it means that our r is equal to 2, and then we also need to find theta. Theta represents the argument of u. So let's sketch a diagram of our problem. We'd have our imaginary axis. This would be the imaginary, and then let's draw a real axis, our real axis, and then we've got -1 in the real axis, so let's put our -1 somewhere here, and then we've got -√3 in the imaginary axis, so let's put -√3 somewhere here, -√3. So our complex number would be at this point here, and we need to find the argument of our complex number. So if I'm just going to draw a line from there to there, it means our argument is the angle formed between the positive real axis and our complex number. So that is the argument of u. That's what we need to find, and we can do that by forming a triangle here. Let's draw a triangle, and then to the origin, and then back to our complex number. This here would be a right angled triangle, and this distance is 1, and we know that this distance here is root 3, and let's call this angle alpha. So to find alpha, we can say that tan alpha is equal to the opposite, which is root 3, over the adjacent, which is 1. So alpha would be arctan of root 3. And arctan of root 3 is, arctan of root 3 gives us, that's 1 over 3 pi. Alpha is equal to 1 over 3 pi. Right, but remember what we are looking for is the argument of u. So we can say that the argument of u is equal to 180 degrees or pi minus the 1 over 3 pi, which would give us that the argument of u is 2/3 pi. But notice how our angle is below the real axis, so this means that our argument is actually negative. So it means that at the end we have to conclude that argu is negative 2/3 pi. If our argument was in these two quadrants, then we'd know that our argument is positive, but because it's in a quadrant that's below the real axis, it is negative. Okay, so it means that theta is the argument of u. Theta is equal to negative 2/3 pi. So we can conclude that therefore u is equal to r, which is 2 cos, our angle is negative 2/3 pi, so cos negative 2/3 pi plus I sine theta, which is negative 2/3 pi. Alright, and we have expressed our argument, and we have expressed our complex number in polar form. Okay, the complex number v is given by v is equal to 5 times cos 1 over 6 pi plus I sine 1 over 6 pi. Part B, express the complex number v over u in the form rei theta, where r is greater than 0 and theta is between negative pi and pi. So what we can do is to take v and u individually and then convert them to rei theta first. So let's start with v. V were given to be 5 times cos 1 over 6 pi plus I sine 1 over 6 pi. So again, we know that this is in the form r cos theta plus I sine theta. So it means that if we want to move to the form rei theta, we only need to know what r is and what theta is. So for v, we know that r is equal to 5, so this is 5 I, and then our theta for v is 1 over 6 pi. So this here would be 1 over 6 pi. Okay, and we'll do the same for u. U, we represented it as 2 cos negative 2/3 pi plus I sine negative 2/3 pi. And so in this case, our r is 2, and then our theta is negative 2/3 pi. And so it means that v over u is equal to our v here, that's 5 I 1 over 6 pi over our u, which is 2 I negative 2/3 pi. So it means to get our modulus here, we're simply saying 5 over 2, that would be r. And then to get our angle theta, here we can tell that these two are powers, right? And if we've got two powers dividing each other, we know that we can subtract them. So that becomes 1 over 6 pi minus 2/3 pi. This is just simply using laws of indices. So this becomes 1 over 6 pi plus 2 over 3 pi, and that gives us 5 over 6 pi. So theta is 5 over 6 pi. And so we can conclude that Do we have space? No, we don't. We can conclude that therefore v over u can be written as re I theta by saying 5 over 2 e I 5 over 6 pi. And this would be our final answer. Number 5. The equation of a curve is y is equal to e to the sine x over cos squared x for x is between 0 and 2 pi. Find dy dx and hence find the x coordinates of the stationary points of the curve. Alright, so we've been given y is equal to e to the sine x over cos squared x. So here we can use the quotient rule. We know that if y is equal to u over v, then dy dx would be that's v du dx minus u dv dx over v squared. Alright, so here we can say let our u be equal to e to the sine x, and then our v is the denominator, so that's the cos squared x, but I'll write it this way because it's easier to differentiate it when it looks like that. So let's find our du dx. So to differentiate e to the sine x, we simply have to find the differential of sine x, and that's going to multiply e to the sine x. So if you differentiate sine x, you get cos x, and that's going to multiply our u, so e to the sine x. And then we need dv dx. To get dv dx, we're going to bring down our power, so that's 2 cos x, and then differentiate the inner function. If you differentiate cos x, you get negative sine x. So dv dx is equal to, that's negative 2 sine x cos x. Alright, so now that we have our du dx and dv dx, we can substitute into our formula for dy dx. So it means dy dx would be equal to, that's v, which is cos squared x multiplied by du, which is cos x e to the sine x minus u, that's e to the sine x, multiplied by dv, which is negative 2 sine x cos x, and this is all being divided by our v squared. So cos squared x becomes cos to the 4x. Alright, so let's just simplify our numerator. So that's dy dx is equal to, for the first term in the numerator, that becomes cos cubed x e to the sine x, and this is, we've got this negative sign here, and then we've got the negative sign there, so it will end up being positive, and this is 2 sine x cos x e to the sine x, and this is all over cos to the 4x. And in our numerator we can factor out cos x e to the sine x since it's common in both terms. So cos x e to the sine x, so it means our first term becomes cos squared x, and then our second term becomes plus 2 sine x, and this is over cos to the 4x, so we can cancel out the cos x, and this here becomes a 3. Alright, so we're saying that dy dx is equal to, that's e to the sine x, and this is being divided by the cos cubed x, and that's multiplied by cos squared x plus 2 sine x. This is our dy dx. Alright, now they've also asked us to find the x coordinates of our stationary points. We know that at a stationary point dy dx is equal to 0. So dy dx must be 0. So we can equate our expression here to 0. So that's e to the sine x over cos cubed x times cos squared x plus 2 sine x is equal to 0. And now we can equate each factor to 0. So e to the sine x over cos cubed x is equal to 0. And we can also say that cos squared x plus 2 sine x is equal to 0. So we can actually further split this into two separate equations, but we'd still end up with no solutions because we'd get 1 cos cubed x is equal to 0, and we'd have e to the sine x is equal to 0. And so dealing with our first equation here, there's no way that we can solve this here, so we'd end up with no solutions from here. We'd end up with no solutions. And then for this one, e to the sine x, to get rid of the exponential, we'd have to apply the natural logarithm to both sides. But if we do that, we also end up with no solutions because ln 0 does not exist. So we also end up with x is no solutions here. X is no solutions, which leaves us with only one equation, which is cos squared x plus 2 sine x is equal to 0. Now for this, we can actually simplify this into a 3-term quadratic in sine x, and we can do that by using the identity cos squared x is identical to 1 minus sine squared x. So it means this becomes 1 minus sine squared x. We're replacing this part here with 1 minus sine squared x plus 2 sine x is equal to 0. Let's multiply through by negative 1 to make our coefficient of sine squared x positive. So sine squared x minus 2 sine x minus 1 is equal to 0. Alright, I don't think we can factorize this by side, so let's use the quadratic formula. Sine x is equal to minus b, so that's 2, plus or minus the square root of b squared, so 2 squared, minus 4a, which is 1, c, which is negative 1, and this is all over 2 times a, which is 1. So we're saying sine x is equal to, let's punch this into the calculator, 2 minus the square root of 2 squared minus 4 times 1 times negative 1 over 2 times 1. So this gives us 1 plus or minus the square root of 2. So let's separate this into two equations. So we've got sine x is equal to 1 minus root 2, and we've got sine x is equal to 1 plus root 2. Let's solve each of them separately. X would be arcsine of 1 minus root 2. X is equal to, let's punch that into the calculator. Are we in radians? I believe we're in radians. Yes, from 0 to 2 pi, so we're in radians. Arcsine of 1 minus root 2, and this gives us, in fact, let's call this our principal value because we are going to use this figure to get other solutions. So our principal value is negative 0.4270785864. Alright, our interval is it equal to, less than or equal to, x should be between, yes, so it's including our limits. X should be between 0 and 2 pi inclusive. Alright, so we need to find all the possible solutions for that interval. We can use the formula PV times -1 to the n plus pi times the n. So we can start at n is equal to 1. At n is equal to 1, that's PV times -1 to the power 1 plus pi times 1, and this gives us, that's our principal value times -1 to the power 1 plus pi, that gives us 3.57. that is in fact within 2 pi because 2 pi is approximately 6.28. we can check to see if we have a solution at n equals 2. So that's PV times -1 to the power 2 plus pi times 2. So that's PV times -1 squared plus pi times 2, and that gives us 5.86. Alright, we will not have a solution at n is equal to 3, but feel free to check. And then in this case here, in this equation, we get x is equal to arcsine of 1 plus root 2. So our principal value would be, that's arcsine of 1 plus root 2, and that gives us an error. So here we should say x has no solutions. No solutions. So we can conclude that therefore our x coordinates are, x is 3.57 and 5.86. I don't think they asked for exact values, or did they? They just said it's fine. Okay, so we can give them correct to 3 significant figures, and that's our final answer. Number 6, part A. By sketching a suitable pair of graphs, show that the equation cosec half x is equal to the exponential of x minus 3 as exactly 1 root denoted by alpha in the interval x is between 0 and pi. Okay, so let's draw our y-axis. This is y, and then our x-axis, and this should run from 0 to, let's say, pi is this point over there. Okay, so we're supposed to sketch 2 graphs, so we'll sketch y is equal to cosec half x, and we'll also sketch y is equal to the exponential of x minus 3. Alright, so let's start with the graph of y equals cosec half x. So that graph stems from the graph of y is equal to sine x. So if I can draw the graph of y is sine x, which looks something like that, bear with me. It means that the graph of cosec x would look like this. Like that. We should have another asymptote at this point, and this here would be pi. Alright, so it would mean that we would only want this part for y is cosec x, but notice this stretch that we have in the x direction. So what it means is that we'd actually have half of that graph between 0 and pi, so it means it would actually end there. So in fact, what you'd have from 0 to 2 pi would look something like this, right? That would be y is cosec half x, and then we want the graph of our exponential function. So this here would be our y-axis, and then our x-axis. In fact, we should probably move a bit to the negative side here, we know that the graph of y is equal to the exponential of x passes through this point where y is equal to 1, and it would look like that, right? But notice how this has been translated by -3 units downwards. So instead it would actually pass through the point at -2, because we've moved this 1 down by 3 units. So 1, 2, 3, meaning that the graph that we would have would be the same graph that we are dealing with. If we extend this downwards, it means our asymptote here would be at this point here, and now it's passing through the point -2, and it's the same shape. This would be y is equal to the exponential of x minus 3. So it means that this here, let's say that's -1, this is -2. It means our function should be starting from this point. So it means that our function would look something like this, right? And this would be y is equal to the exponential of x minus 3, and this is y is equal to cosec half x. And we can clearly tell that there is only one point of intersection between 0 and pi, and that means that there is only one root alpha. Okay, so part B says verify by calculation that alpha lies between 1 and 2. So we've been given cosec half x is equal to the exponential of x minus 3. Let's put all the terms on one side and let's call this function f of x. So let f of x equal to cosec half x minus the exponential, and then that becomes a positive 3. And we need to evaluate f of 1 and f of 2. So f of 1 would be cosec, that's half times 1, minus the exponential of 1 plus 3. Let's punch that into the calculator. Remember, cosec is the same as 1 over sine, so that's 1 over sine 1 over 2 times 1 minus the exponential of 1 plus 3, and that's 2.36 and so on. And then we also need to evaluate f of 2, so that's cosec 1 over 2 times 2 minus the exponential of 2 plus 3, so that's 1 over sine half times 2 minus the exponential of 2 plus 3, and this gives us -3.20 and so on. So the thing that we're looking for is a change in sign. Here we got a positive result, and here we got a negative result. So it means that a root lies between 1 and 2. So we can conclude that, therefore, since there is a change in sign, a root, or in this case alpha, since our root is called alpha, alpha lies between 1 and 2. Part C. Show that if a sequence of values in the interval x is between 0 and pi, given by the iterative formula xn plus 1 is equal to ln cosec half xn plus 3 converges, then it converges to alpha. Alright, so what they're basically asking you to do here is to show that this equation is the same as the original equation that they gave us here. So let me just write that equation down. That was cosec half x is equal to the exponential of x minus 3. So we have to show that these two equations are the same. So I'm just going to rewrite this equation here, except I'm going to remove all the n's and n plus 1. So that's x is equal to ln cosec half x plus 3. Now notice how we've got a ln on this side. The only way we end up with ln is if we're to make the x that's on the exponential the subject of the formula. So let's do that here. So e to the x is equal to, that will be cosec half x, move the negative 3 to that side, it becomes a positive 3. Now to get rid of the exponential function, we take the natural logarithm on both sides. So x is equal to the natural logarithm of cosec half x plus 3. And we have proved that these two equations are indeed the same. And then part D goes on to say, use this iterative formula with an initial value of 1.4 to determine alpha correct to 2 decimal places. Alright, so iterative formula is xn plus 1 is equal to ln, that's cosec half x plus 3. Alright, so we've been given our initial value to be 1.4, so let x0 be 1.4. Now let's carry out the first iteration. x1 is ln cosec half times 1.4 plus 3. Let's punch this into the calculator. That's ln. Remember, cosec is 1 over sine, and this is half times 1.4 plus 3, and this gives us 1.5156 correct to 4 decimal places. Our second iteration is ln cosec, that's half, and I want you to replace the 1.4 in your calculator with the ans, that's the answer button on your calculator. It's usually written ans, and you should find it next to your equal sign button. This is plus 3 is equal to, so let me do that. I'm replacing the 1.4 with ans, and then once you've done that, simply press equals, and then you get the result of your iteration. That's 1.4940. Let's move on to the next iteration. Do not change anything on your calculator, simply press equals, and you get the result of our third iteration. So that's 1.4978 correct to 4 decimal places. And then the fourth iteration, press equals, don't change anything else, and you get 1.4971, and we have found our root alpha. So that's 1.50, and so you can conclude that therefore alpha is 1.50, and that's our final answer. Part E says, state the minimum number of calculated iterations needed with this initial value to determine alpha. So we needed a total of 4 iterations to get our correct answer. So we can say that the minimum number of calculated iterations is 4. Number 7, part A. On a single Argand diagram, sketch the loci given by the equations the modulus of z minus 3 plus 2i is equal to 2, and the modulus of w minus 3 plus 2i is equal to the modulus of w plus 3 minus 4i, where z and w are complex numbers. Alright, so let's draw our complex plane. So this is our imaginary axis, and then we need a real axis. So this is our real axis. Let's start with this first equation here. We're given the modulus of z. I'm going to factor out a negative sign here so we can see the point that we're working with. That's 3 minus 2i, and this is equal to 2. So what this means is that we want a circle with the center 3, -2i and a radius of 2 units. Okay, so our circle should have the center 3, -2i, that's -2i, so let's say that somewhere here, and our center would be right there, and this is a circle. Alright, let's shrink it slightly, it's a bit too big, and then let's see if we can make it look decent. Alright, so there's our circle with center 3, -2i and a radius of 2 units. Okay, so that's the first equation. Then let's look at the second equation. And again, I'm going to factor out a negative sign so I can see what the point is. There would have 3 minus 2i again, so that's the same point as the one above. And this is equal to the modulus of w minus, this would be -3 plus 4i. So let's plot the 2 points that we have. We've got 3, -2i, which is the center over there, we already have it, and then we've got the point -3, 4i. Okay, so I'm just going to use a different color. So our first point is the center of this circle, and then our second point is at -3, 4i, so -3 would be somewhere here, and then it's 4 units on the positive imaginary axis, so 4i, that should be somewhere there. So the point that we're looking at is here. And so this equation means that we want the perpendicular bisector of the line that joins these 2 points, right? So let's join our 2 points. So let's join our 2 points, right? And what we want is the perpendicular bisector of this line. So to get that bisector, you'd have to use your compass and draw your construction axe. I do not have a compass with me, so I am just going to do this by sight, but you should use your compass to get accurate construction axe so that you can get a good bisector. Alright, so I think our bisector should be somewhere here, and this here should be 90 degrees. Notice that this question is a bit different from previous ones because they typically bring inequalities, but in this case they've put equal signs. So for this one, for example, we are looking for the points that are in equal distance from the point -3, 2i and the point 3, -4i. So those are all the points that lie on our green bisector. They satisfy that equation. And then for this one, we are looking for the points that are equal to the radius of the circle. In other words, the points that lie on the circumference of the circle. So just by drawing this, we have satisfied the Argand diagram that they are looking for. Part B, hence find the least value of the modulus of z minus w for points on these loci. Give your answer in an exact form. Now if we go back to our part A, you notice that our first equation here is for z, so it means that z would be all the points that are on the circumference of the circle, and then w is all the points that lie on the perpendicular bisector. So if we're saying the modulus of z minus w, remember modulus is the distance or the magnitude. In this case, we're looking for the shortest, the shortest distance from z, which we said is the circumference, to the perpendicular bisector. So the shortest distance would be the distance from our circumference to the bisector at this point, because we can tell that if we take it at any other point, for example this point over here, the distance is greater, it's not the shortest distance, right? So it means we need to find that distance over there. We can get the distance of this blue part by saying the distance from the center of the circle to our perpendicular bisector minus this red radius that you see. It should give us this blue line. Okay, so we need to first find the distance from the center of the circle to the perpendicular bisector. And since this is a perpendicular bisector, that distance should be half of this red line that we have over here. So we know that our points here are, that is -3, 4, 4i, this is a comma, and then here our points are 3, -2i. Okay, so we need to first find the length of that line. So that line would have a length of, that's the square root of, that's 3 minus -3, so plus 3 squared plus -2 minus 4 squared. We're just using the equation for length of a line between 2 points. And so if we punch this into the calculator, that's the square root of 3 plus 3 squared plus -2 -4 squared. And that gives us, that is 6 root 2. 6 root 2. But remember, what we want is in fact the distance from the center to the perpendicular bisector. So from the center to the green line, which is half this distance. So we want half of 6 root 2, which gives us 3 root 2. Okay, so we're saying the distance from the center to the perpendicular bisector is 3 root 2, and we have to subtract the red radius over here if we want to get the distance of the blue line. So that's -2, and that gives us our final answer. The shortest distance from Z to W is from the circumference to the green perpendicular bisector, and we can get that from 3 root 2 minus 2. Number 8. Use the substitution u equals 1 minus sine x to find the exact value of the integral from pi to 3 over 2 pi of sine 2x over root 1 minus sine x with respect to x. Give your answer in the form a plus b root 2, where a and b are rational numbers to be determined. Okay, so we are integrating from pi to 3 over 2 pi, and this is sine 2x over the square root of 1 minus sine x with respect to x, and we've been given the substitution u is equal to 1 minus sine x. So straight away we can replace this 1 minus sine x with u and write this as the integral from pi to 3 over 2 pi of sine 2x over root u, and this is with respect to x. Now let's work on our limits. We want to convert them to u. So we've been given u is 1 minus sine x, and let's evaluate u at x is 3 over 2 pi. So that's u is equal to 1 minus sine 3 over 2 pi. U is equal to, that's 1 minus sine 3 over 2 pi, and that gives us u is 2, and then at x is equal to pi, that's the lower limit, u is equal to 1 minus sine pi. U is equal to, that would give us a 1 since sine pi is 0. Okay, so our new limits are from 1 to 2, and we're integrating sine 2x over root u. Now we need to work on our dx. So our substitution is u is 1 minus sine x. Let's differentiate that. So du dx would give us, if you differentiate 1, that's a constant, so it gives us 0. And then if you differentiate negative sine x, you get negative cos x. So that's negative cos x. And we want dx. So dx would be equal to negative 1 over cos x du. So we're going to substitute our dx over here with negative 1 over cos x du. So that's the integral from 1 to 2 of sine 2x over root u multiplied by negative 1 over cos x du. And now this step is where you have to be a little bit clever. You're going to convert this using a double angle formula. So sine 2x, we know that can be written as 2 sine x cos x, right? So that means what we have here is the integral from 1 to 2 of 2 sine x cos x, and this is over root u multiplied by our negative 1 over cos x du. And so this cos x would cancel with that cos x, and so it means we've got the integral from 1 to 2 of, I'll put the negative 2 outside, and this is sine x over root u, and this is with respect to u. Okay, and finally we have to get rid of the sine x that we have here. That's the last thing that is in terms of x. Okay, so our substitution is u is 1 minus sine x. So we need to make sine x subject of the formula. So sine x would be equal to 1 minus u. And so this here can be written as negative 2, the integral from 1 to 2 of, we're replacing sine x with 1 minus u. So 1 minus u over the square root of u, but I'll write that as u to the power half with respect to u. And now everything is in terms of u, but we want to distribute the denominator so that we simplify. So this is the integral from 1 to 2 of 1 over u to the half minus u over u to the half with respect to u. Alright, so that's negative 2, the integral from 1 to 2 of, this is u to the negative half, and then there that would be root u or u to the half, because that's 1 minus half, so u to the half, and this is all with respect to u. We can now finally integrate. Okay, so we've got our negative 2, and then let's add 1 to negative half, we get a positive half, so u to the half divided by half, so that's multiplied by 2, minus u to the half, so add 1 to the power, that becomes 3 over 2, divide by 3 over 2, that's multiplying by 2 over 3, and our limits are from 1 to 2. Okay, so let's substitute in our limits. We'll start with the upper limit, so that's 2 times 2 to the half minus 2 over 3, 2 to the 3 over 2, and then our lower limit, that's 2 times 1 to the half minus 2 over 3, that's 1 to the 3 over 2. Okay, and now let's simplify. That's negative 2. Okay, so remember that in the stem of the question they want their answer in the form a plus b root 2. So our calculator is not going to save us. We're going to have to do this manually. So that's 2 root 2, 2 root 2 minus 2/3 times, we can write 2 to the power 3 over 2 as 2 to the power half times 3, and then for our lower limit, that's 2 minus 2 over 3. So let's continue to simplify. We've got 2 root 2 minus 2/3, that is root 2, and this is cubed. In fact, we can write our root 2 cubed. Root 2 cubed would be the same as, that's root 2 times root 2 times root 2, and this can be written as these 2 times 2, 2 times 2, and we'll keep that this other root 2 outside. And we know that this here is root 4 times root 2, so that is 2 root 2. Okay, so that means we can replace our root 2 cubed here with 2 root 2. So what we have here is times 2 root 2, and that's 2 minus 2/3, that would be 2 minus 2/3, that's minus 4 over 3. Be careful with the negative sign here. Okay, and let's continue to simplify. So that's negative 2 times, we've got, that's 2 root 2 minus, that's 4/3 root 2 minus 4/3, so that's negative 2, and we've got 2 minus 4/3, so this is 2/3 root 2 minus 4/3, and then we can multiply through by 2 to get negative 4/3 root 2 plus 8 over 3, and this here is our final answer. In fact, we should probably swap it because they say they want it in the form a plus b root 2, a plus b root 2, so the 8 over 3 should come first. 8 over 3 minus 4 over 3 root 2. Number 9. The equations of two straight lines L1 and L2 are L1 is equal to R equals I minus 2j plus 3k plus lambda times 2i minus j plus ak, and L2 is R is equal to negative I negative j negative k plus mu times 3i minus 2j minus 2k, where a is a constant. The lines L1 and L2 are perpendicular. So if we have two lines that are perpendicular, we know that their dot product or scalar product is equal to 0, okay? Or rather, the dot product of their direction vectors is equal to 0. So I'm just going to write them as column vectors because I think it's a bit clearer that way. So the first direction vector is 2 minus 1a, and we want the dot product, so that's 3 minus 2 minus 2, 3 minus 2 minus 2, and this should be equal to 0. So that's 2 times 3 plus negative 1 times negative 2 plus a times negative 2, and this should be 0. So 6 plus 2 minus 2a is equal to 0. 8 minus 2a is equal to 0. 2a is equal to 8. Divide both sides by 2. You get that therefore a is indeed 4. The lines L1 and L2 also intersect. Find the position vector of the point of intersection. Alright, so what are the equations of our lines? So we've got L1, let me just write that down. L1 is R is equal to, I'll write it as a column vector again, 1 minus 2 plus 3, 1 minus 2, then 3 plus lambda, and the direction vector is 2 minus 1, a, we said a is 4. Alright, and then we've got L2, which is R is equal to, that's minus 1 minus 1 minus 1. Alright, so minus 1 minus 1 minus 1 plus mu, our mu is 3 negative, our direction vector rather, 3 negative 2 negative 2, 3 negative 2 negative 2. Okay, and we have been told that these two lines intersect and we want the position vector of the point of intersection. So if you have two lines and you want their point of intersection, you solve simultaneously. So that's what we're going to do. From our first equation, L1, we can get three equations. So the first one is 1 plus 2 lambda, 1 plus 2 lambda, and that would match negative 1 plus 3 mu, negative 1 plus 3 mu. And then the second one is negative 2 minus lambda, negative 2 minus lambda would be equal to negative 1 minus 2 mu, negative 1 minus 2 mu. And then the third one is 3 plus 4 lambda, 3 plus 4 lambda, and this is equal to negative 1 minus 2 mu, negative 1 minus 2 mu. Alright, so let's take our second equation and we want to make lambda the subject of the formula. So we've got negative 2 negative lambda is equal to negative 1 negative 2 mu. So lambda must be equal to, that's negative 2 plus 1 plus 2 mu. So if we simplify that, we've run out of space. We know that our lambda should be equal to negative 1 plus 2 mu. And then we can substitute this into the first equation so that we can solve for mu. So we've got 1 plus 2 lambda, and our lambda is negative 1 plus 2 mu, and this is equal to negative 1 plus 3 mu. So that's 1 minus 2 plus 4 mu is equal to negative 1 plus 3 mu. Okay, so that's negative 1 plus 4 mu is equal to negative 1 plus 3 mu, and we want to make mu the subject of the formula, so that's 4 mu minus 3 mu is equal to negative 1 plus 1. So in this case we get that mu is equal to 0. Alright, so here we could go ahead and solve for lambda, but that doesn't help us. What we want to find is simply the position vector of the point of intersection. So let's just draw a picture of what we're working with here. First of all, we know that our lines L1 and L2 are perpendicular, so we're looking at something that looks like this, right? This would be L1 and this is L2, and they are perpendicular, and then we are looking for their point of intersection. So in this case, we know that since we found mu, right, we found mu to be 0, we can simply use the formula that has mu, and that's L2, to give us the coordinates of this point of intersection. We know that this point is the point at which mu is equal to 0. So we can simply substitute mu is equal to 0 into the equation of that line. So we've got r is negative 1, negative 1, negative 1 plus mu, and our direction vector is 3, negative 2, negative 2. And so the general coordinates of any point that lie on this line would be negative 1 plus 3 mu, negative 1 minus 2 mu, and negative 1 minus 2 mu. And we know that the point that we want is the point at which mu is 0, so we can simply substitute mu with 0, so that's negative 1 plus 3 times 0, negative 1 minus 2 times 0, negative 1 minus 2 times 0, and so this leads to negative 1, negative 1, negative 1. That is the point of intersection of our two lines. So we can say that therefore this is negative 1, negative 1, negative 1, and that's our final answer. The point A has position vector negative 5i plus j minus 9k. Part C, show that A lies on L1. So what is the equation of L1? L1 is r is equal to 1 minus 2, 3, 1 minus 2, 3 plus lambda, and our direction vector is 2, negative 1, 4. 2, negative 1, 4. Alright, and so the general coordinates of any point that lie on this line are 1 plus 2 lambda, 1 plus 2 lambda, negative 2 minus lambda, negative 2 minus lambda, 3 plus 4 lambda, 3 plus 4 lambda. And we have been given the point with the coordinates negative 5, 1, negative 9. And we have to verify that this point lies on this line. So what we can do is we can equate our x coordinate, the negative 5 part, to the x coordinate of the general point that lies on the line. So 1 plus 2 lambda is equal to negative 5. And let's solve for lambda. 2 lambda is negative 6. So divide both sides by 2. Lambda is negative 3. So if we substitute this value of lambda is negative 3 into these two expressions over here, we should get 1 and negative 9 if A does in fact lie on the line L1. So let's do that. Alright, so the general coordinates of any point are 1 plus 2 lambda minus 2 minus lambda, 3 plus 4 lambda. So if A does in fact lie on this point, we should get the coordinates for A when we substitute lambda is negative 3. So 1 plus 2 times negative 3, negative 2, negative 3. And then we've got 3 plus 4 times negative 3. Okay, so the first one is 1 minus 6, and that gives us negative 5. The second one is negative 2 plus 3, that gives us a positive 1. And the last one is 3 minus 12, which gives us a negative 9. And this shows that A does in fact lie on L1 because it gave us the correct coordinates. The point B is the image of A after reflection in the line L2. Find the position vector of B. Okay, so remember that the situation that we have is that L1 and L2 are perpendicular, right? So let's say this is L1. It must mean that this here would be L2, right? And we know that we've got our point A lying on the line L1. If we go back to part C, we know that A lies on L1. So we can assume that, let's say A is this point here. So we're saying that's A, and we said A has the coordinates negative 5, 1, negative 9. Negative 5, 1, negative 9. So that's A. And we also know the points of intersection. So I'll call this point, let's call it point X. And we calculated the point of intersection rather. We calculated here in part B, and we got negative 1, negative 1, negative 1. Alright, so we know that that has the coordinates negative 1, negative 1, negative 1. Okay, and then we've been told that B is the image of A after it has been reflected in the line L2. So if we reflect A in the line L2, B would be somewhere here. And from here we can create an equation that we can use to help us to solve for B. We can tell that the midpoint of the line AB is X. So in other words, we're saying the distance from A to X is equal to the distance from X to B. Or we can write this as the vector AX must be equal to the vector XB, right? And so if we simplify this, this can be written as AX is equal to OB minus OX, right? And what we're looking for is the position vector of OB. So we can make OB the subject of the formula. OB is equal to, that is AX plus OX. We already know that OX is negative 1, negative 1, negative 1. What we need to find is our AX. Okay, so let's do that on the side here. AX would be equal to OX minus OA, right? So AX is equal to, our OX is the negative 1, negative 1, negative 1, and this is minus our OA, which is negative 5, 1, negative 9. So that means AX here is negative 1, negative negative 5, so that's 5 minus 1, which is 4. Then we've got negative 1, negative 1, which is negative 2. Then we've got negative 1 minus minus 9, so 9 minus 1, that gives us an 8. So this is AX. Now that we have both AX and OX, we can find what OB is. OB is equal to AX, which is 4 minus 2, 8, plus OX, which is negative 1, negative 1, negative 1. So therefore, our OB must be equal to 4 minus 1, which is 3, negative 2, negative 1, which is negative 3, 8 minus 1, which is 7. And this here would be our final answer. Number 10, part A. Given that 2x is equal to tan y, show that dy dx is equal to 2 over 1 plus 4x squared. Alright, so we've been given 2x is equal to tan y, and we have to find dy dx. So we can differentiate this implicitly, right? This is with respect to x. So if you differentiate 2x, you're going to get a 2. And if you differentiate tan y, you get sec squared y dy dx, right? Don't forget the dy dx. So it means that our dy dx is equal to 2 over sec squared y. Now you can see we've already got the numerator that they're looking for. The only difference is that our denominator is different from their denominator. So we have to find a way to rewrite sec squared y as 1 plus 4x squared. And we can do that by going back to our original equation here. We've got 2x is equal to tan y. Let's square both sides. So 2x squared is equal to tan y squared. So this becomes 2 squared x squared, and this is tan squared y. We want to find an identity that relates tan squared y to sec squared y, and that identity is 1 plus tan squared y is equal to sec squared y. So we can write this as tan squared y is equal to sec squared y minus 1. So you can replace this tan squared y with sec squared y minus 1. So what we end up with is 4x squared is equal to sec squared y minus 1. And so now let's make sec squared y subject of the formula here. Sec squared y is equal to 1 plus 4x squared. So we can replace this sec squared y with 1 plus 4x squared. So what we end up with is dy dx is equal to 2 over 1 plus 4x squared. And that is exactly what they're looking for. Part B. Hence find the exact value of the integral from half to root 3 over 2 x arctan of 2x with respect to x. So we're integrating by parts here, and in this case we'll choose our u to be arctan of 2x because we know how to differentiate that. If you don't see how we can differentiate that, I'll explain that in a second. And then our dv dx would be our x. Now if we go back to our part A, we're given that 2x is equal to tan y. Notice how I can easily rewrite 2x is equal to tan y as y is equal to arctan of 2x. If you apply arctan to both sides, this can be written as y is equal to arctan 2x. And we know that our 2x is equal to arctan y leads to our dy dx being equal to 2 over 1 plus 4x squared. And so since we've shown that 2x is equal to tan y is the same as y is equal to arctan of 2x, it means they must have the same differential. So we know that the differential of y is equal to arctan of x is dy dx is 2 over 1 plus 4x squared. So in other words here, our du dx is 2 over 1 plus 4x squared. Alright, and then here we can integrate to get v, add 1 to the power, that's 2, divide by the new power, that's half x squared. Okay, and so it means that the integral of x, I'll ignore the limits for now, arctan 2x with respect to x is equal to uv, so that's half x squared arctan of 2x minus the integral of v du, so half x squared multiplied by 2 over 1 plus 4x squared, and this is all with respect to x, right? And I want to take our focus to this part over here. So we've got the integral of half x squared times 2 over 1 plus 4x squared with respect to x. The half cancels out with this 2, so what we end up with is the integral of x squared over 1 plus 4x squared with respect to x. Okay, and we have to integrate this function. Now it's very difficult for us to integrate that function directly, and so we can consider that this is a rational function, right? And if you've got a rational function in which the highest power in the denominator is equal to the highest power in the numerator, this is an improper fraction. So we want to decompose into partial fractions considering that this is an improper fraction. So use the method that you use to decompose into partial fractions when you have an improper fraction. I know some people prefer to do long division. I'm not going to carry out long division. The way I do it is we want to write our numerator in terms of the denominator. So our denominator is 1 plus 4x squared. And then I want to multiply our bracket here by a number that will make this 4x squared equal to x squared. So what I'm saying is that we've got a number, let's call that a, that when it is multiplied by 4x squared, it should give us x squared. So obviously that number would be a quarter, because a quarter times 4x squared should give us x squared. So we multiply our bracket by a quarter, right? But remember, our numerator still has to be equal to this numerator over here. So we know that a quarter times 4x squared gives us x squared. But when we expand our bracket, we also get a quarter times 1. So we need to get rid of that 1 quarter, so that when this whole numerator is expanded, in fact we can do it at the bottom here, a quarter times 1 plus 4x squared minus a quarter, so that's a quarter plus x squared minus a quarter. We can tell that the quarter will cancel out with the minus a quarter, and we end up with our original numerator of just x squared. Alright, so now that that's out of the way, we can go ahead and distribute our denominator. So this is a quarter times 1 plus 4x squared divided by our denominator 1 plus 4x squared minus this 1 over 4, and that is being divided by our denominator of 1 plus 4x squared. Alright, so this here will cancel out and we end up with a quarter, and then what we have here is minus 1 over 4 times 1 plus 4x squared. Okay, alright, and we're saying that this here is equal to x squared over 1 plus 4x squared. In fact, I think let's just factor out the 1 over 4, so that that's 1 minus 1 over 1 plus 4x squared. Okay, and so it means we are integrating 1 over 4, 1 minus 1 over 1 plus 4x squared with respect to x. Let's take the quarter outside the integral sign. So that's a quarter, 1 minus 1 over. This can be written as, I'll start with the 4x squared part, but I'll write it as 2x squared, and this is plus 1 squared, and this is with respect to x. I'll explain why I've done that in just a bit. And now we can integrate. If you integrate the 1, you get an x minus, now let's focus on our second term here. If you go to your MF19, we've got the integral of 1 over x squared plus a squared with respect to x, and that should give us 1 over a arctan of, that's x over a. 1 over a, in this case our a is 1, but notice how we've got 2x instead of x, so it means we also have to divide by that 2 over there, and that's arctan of, that's x, so in this case that's 2x divided by a is 1. Alright, so this simplifies to give us a quarter x minus 1 over 8 arctan of 2x. Okay, so this here is the integral of this part over here. So we can simply rewrite everything and then replace this part with its integral. So this is the integral of x arctan 2x with respect to x, and it's equal to half x squared arctan 2x minus this part over here. So that's a quarter x minus 1 over 8 arctan 2x. Alright, so let's simplify that. That is half x squared arctan 2x minus a quarter x plus 1 over 8, be careful with the negative signs, arctan 2x. And now we can bring back our limits. What are our limits? They are half and root 3 over 2. So we're integrating from half to root 3 over 2. So we can substitute them in. So we'll start with our upper limit. So that's 1 over 2 times root 3 over 2 squared arctan of, that's 2 times root 3 over 2 minus a quarter x, so that's a quarter root 3 over 2 plus 1 over 8 arctan, that's 2 times root 3 over 2. Okay, be careful with the brackets, there are a lot of brackets here. And let's do the lower limit. So that is half times half squared arctan of 2 times half minus a quarter times half plus 1 over 8 arctan of 2 times half. Okay, now we need to evaluate what this simplifies to. So let's start with 1 over 2 times, that's root 3 over 2 squared. This part over here gives us a 3 over 8. Right, and now we need to evaluate arctan of 2 root 3 over 2. So that's arctan of root 3, and that gives us a third pi. And now we need to evaluate negative 1 over 4 times root 3 over 2, and that gives us negative root 3 over 8. Okay, and then we've got plus 1 over 8 arctan of root 3, so that's a third pi. And now we go on to our lower limit, so we've got half times half squared, so that's half times a quarter, which is 1 over 8, and that's arctan of 1, which is a quarter pi. And then we've got negative a quarter times half, so that's negative 1 over 8. And finally we've got that 1 over 8 multiplied by arctan of 1. Arctan of 1 is a quarter pi. Alright, and now let's simplify this even further. So here our 3's will cancel out, so that we have pi over 8. And then we've got minus root 3 over 8 plus 1 over 24 pi minus 1 over 32 pi minus 1 over 8 plus, that's 1 over 32 pi. Alright, let's simplify further. So we've got pi over 8 plus, so we've got pi over 8 plus 1 over 24 pi. So let's find the coefficient. That's 1 over 8 plus 1 over 24. That gives us 1 over 6 pi minus root 3 over 8. Then let's expand our bracket here. So that's minus 1 over 32 pi plus 1 over 8 minus 1 over 32 pi. So let's simplify everything that has pi. So that's 1 over 6 minus 1 over 32 minus 1 over 32, and that gives us 5 over 48 pi minus our root 3 over 8 plus our 1 over 8. And that there is our final answer. We have given the integral as an exact value. Number 11. In a field there are 300 plants of a certain species, all of which are infected by a particular disease. At time t after the first plant is infected, there are x infected plants. The rate of change of x is proportional to the product of the number of plants infected and the number of plants that are not yet infected. The variables x and t are treated as continuous, and it is given that dx dt is equal to 0.2 and x is equal to 1 when t is 0. Part A. Show that x and t satisfy the differential equation 1495 dx dt is equal to x times 300 minus x. Okay, so we are told that x represents infected plants, right? X is our infected plants. Infected plants, if I can write that properly. So plants, and then we also have t, which is the time after first plant, time after first infection, or after first plant is infected, first infection, right? Then they go on to tell us that the rate of change of x, which we can write as dx dt, is proportional, so we can put the proportional sign, to the product of the number of plants infected, so that's x. They say product, so multiply, and the number of plants that are not yet infected. So the number of plants not yet infected would be the total number of plants, 300, minus the number of infected plants, x. Alright, okay, so if we remove the sign for proportionality, we can write this as dx dt is equal to our constant of proportionality times x times 300 minus x. Alright, and then at this stage we need to find what k is. and we can use the information that they've given us here, that dx dt is 0.2 when our x is 1, and this is at time t is 0, 300 minus 1. Okay, so let's simplify and solve for k. So 0.2 is equal to, that is 299k. So k would be equal to 0.2 over 299. Let's punch that into the calculator. 0.2 divided by 299 gives us k is equal to 1 over 1495. So it means that we have dx dt is equal to our k, which is 1 over 1495, and this is multiplying the x times 300 minus x. Okay, and we have to show that it is the same as this equation, so we can multiply both sides by 1495, and so this becomes 1495 dx dt is equal to x times 300 minus x, and this here is our final answer. Part B. Using partial fractions, solve the differential equation and obtain an expression for t in terms of a single logarithm involving x. Alright, so what is our dE? We've got 1495 dx dt is equal to x times 300 minus x. Okay, so we can separate our variables and put everything that is x on the left hand side. So what we end up with is 1495 over x times 300 minus x dx is equal to dt. Okay, so what we want to do is we want to use partial fractions to decompose this function that we have. So we want to decompose our rational function over here to its partial fractions. So let's do that on the side. So that is 1495 over x times 300 minus x. So we've got two linear factors over here. So this can be written as a over x plus b over 300 minus x. Alright, so if we multiply through by x times 300 minus x to get rid of all the denominators, this becomes a times 300 minus x plus b times x. Alright, now we need to find both a and b. Let's start with a. We can find a by saying let x equals 0, because if you multiply b by 0 it gives us a 0, yeah? So this is 1495 is equal to a times 300 minus our x, which is 0. So we get 300a is equal to 1495. So a is 1495 over 300. If we punch that into the calculator, that gives us 299 over 60. Alright, and now we need to find what b is. So we can say let x equal 300, because if you substitute x with 300 here, this whole expression becomes a 0, and we can evaluate our b. So that gives us 1495 is equal to 300b. And so that means b would also be the same as a, so that's 299 over 60. Alright, so that means our original fraction over there, the 1495 over x times 300 minus x, can be written as, we've got 299 over 60 being divided by x plus 299 over 60 being divided by 300 minus x. Now just to make things a bit clearer, I'm going to factor out the 299 over 60 so that this here becomes 299 over 60 multiplied by 1 over x plus 1 over 300 minus x. Right, and we can go back to our equation and say that the left hand side can be written as 299 over 60 times 1 over x minus, right, minus or plus, it's plus 1 over 300 minus x with respect to x, and this is equal to dt. And now we have to integrate both sides. I'll take our 299 over 60 outside of our integral sign, and then here we are integrating 1 with respect to t. So let's integrate both sides. So on the left hand side we've got 299 over 60, and then if you integrate 1 over x you get ln x. If you integrate 1 over 300 minus x you get negative ln 300 minus x plus a constant of integration, and this is equal to, if you integrate 1 you get t. So now we need to find what our constant of integration is, and we can use the information we were given that x is 1 when t is 0. Alright, so x is 1 when t is 0, which gives us 299 over 60 times ln 1 minus ln 300 minus 1 plus c is equal to 0. Okay, so that gives us 299 over 60, ln 1 is 0, so that's minus ln 299 plus c is equal to 0. So c is 299 over 60 ln 299. So we can write our equation as, I'll just put this t on the left hand side, as t is equal to 299 over 60 times ln x minus ln 300 minus x, and we can even factor out the 299 over 60 from the c so that we've got plus ln 299 here, and that there is our differential equation. They say that they want us to write this as a single logarithm. Okay, so we can use laws of logarithms here. So I'm just going to rearrange this a bit. T is equal to 299 over 60 times ln x, then I'll write the ln 299 second, ln 299 minus ln 300 minus x. And now we can use the laws of logarithms. We know that ln a plus ln b is equal to ln ab, and we know that ln a minus ln b is equal to ln a over b, and we're going to use these two to help us simplify what we have here. So this then becomes t is equal to, that's 299 over 60 ln, so these two are adding, so they must multiply 299x, and then this one is subtracting, so it must divide 300 minus x. Alright, and this here would be our final differential equation. And I believe that is the end of the paper. Yes, it is. Alright, so if you found this video useful, please leave a like and subscribe for more videos like this. Bye bye.